Welcome back, everyone, to our ongoing series on data structures and algorithms here on CSAITTL. Today, we're tackling a classic engineering challenge string pattern matching. We're all used to Command F and Control F to find a word in a document. But have you ever wondered how the computer does it so fast? Most beginners starts with a knife search, which is painfully slow. Today, we are going to debug exactly why that knife search fails and introduce two heavy hitters in the algorithm world, KMP and Rabin-Karp. KMP uses structured memory and prefix functions to avoid backtracking, while Rabin-Karp uses the mathematical magic of rolling hashes. By the end of this session, you'll understand the how and the why behind these high-performance tools. If you're preparing for a technical interview or just want to write a better code, you're in the right place. Don't forget to follow, like the video, and hit the notification icon to stay updated on our DSA journey. Before we look at the code, let's build a mental model using what I call the novel analogy. Imagine you are reading a 500-page book and you're looking for the name Elizabeth. If you use naive reading, your eyes scan every single the and it in the page. If you say an E, you check the next letter. If it is an L, you keep going. But if you hit a T instead of an L, I, the naive way says you have to go back to exactly where you started and try again. Humans don't do that. Instead, we use efficient scanning. If we see a Z in the middle of the word, we immediately know Elizabeth can't be there, and we skip ahead. We use memory. We remember what we saw, and we use structure. If the word starts with ELI, and we fail at the Z, we don't necessarily need to restart from the beginning of the sentence. This is the core insight. Computer should mimic this human behavior by utilizing memory and the inherent structure of the pattern to skip redundant work. Let's look at the broken state of the knife search to see why it scaled so poorly. Suppose we are searching for the pattern A in a long string of A's. In this visual, the text has 5 A's followed by some other characters. Our pattern matches the first 4 characters perfectly, but when we get the fifth character, the match fails. What does that knife search do? It shifts the pattern by exactly one position. It then immediately rechecks the 3 A's it just looked at. This is the pain point. We are constantly re-verifying information we already know. In the worst case scenario, like searching for a long pattern in a text full of similar character, the cost is O n by m, where n is the text length and m is the pattern length. On a large scale, this redundancy is a performance killer. We need a way to ensure that once we have looked at the character in the text, we never have to look at it again. This brings to our first major solution, the KMP Insight. The genius of Knuth-Morris-Pratt was realizing that the pattern itself has a memory. Look at the pattern ABABC. Notice the cell similarity. The start of the pattern AB actually repeats later on. KMP exploits this. If we are matching ABABC and we fail at the C, we don't just give up and restart. We look at what we match right before the failure, ABAB part. Because we know we just saw AB at the end of a successful segment, we know AB is also at the beginning of our pattern. We can simply align the start of the pattern with that ABAB we just found in the text. We don't restart from index 0. We align to the known prefix. We are using the pattern own structure to tell us exactly how far we can safely jump forward without missing a potential match. To make these jumps, KMP uses a specific tool called LPS array. LPS stands for longest prefix, that is also a suffix. Think of this array as a lookup table for the cheat sheet for the computer. For every position in our pattern, we pre-calculate a value. This value tells us if you failed right after this character, here is the length of the longest part of the pattern you've already seen. That can serve as a new starting point. On this whiteboard that you see here, we have a pattern ABABC index 0 to 4. In the next slide, we'll fill in these LPS values. This table is the secret sauce that allows KMP to make decisions in constant time during the search. It eliminates guessing. When a mismatch occurs, the algorithm looks at the LPS value of the previous character and knows exactly where to shift the pattern. No more backtracking, no more redundant check. Let's trace the construction of LPS array by ABC step by step. This is the processing phase. First, for the single character A, there is no proper prefix or suffix, so the value is 0. For AB, the suffix B doesn't match the prefix A, so we stay at 0. Now look at ABA. It ends with an A and starts with an A. That's a match. The length of this matching part is 1. For ABAB, the suffix is AB and the prefix is AB. That's a match of length 2. Finally, for ABABC, the C breaks the pattern of ABs. So we drop back to 0. Our final array is 0, 0, 1, 2, 0. Look at that 2 at index 3. It tells the computer, if you fail at index 4, which is the C, you don't need to restart. You already have a matching prefix of length 2 ready to go. This pre-processing only takes OM time, which is the tiny price to pay for the efficiency we gain later. Now, let's see the jump in action. This is the fallback move that makes KMP so fast. Imagine our text starts with ABABA and our pattern is ABABC. We match ABAB perfectly. Then we hit a mismatch at the C. In a naive search, we would rewind the text pointer all the way back to the second A. In KMP, we look at our LPS array. For the character before our failure, which is at index 3, the LPS value was 2. This 2 tells us that we can keep or we can keep the first two characters of our pattern AB aligned with the text we just saw. We slide the pattern forward, but here is the most important part. We did not rewind the text pointer. The text pointer stays where the mismatch happened, and we just try the new pattern character against it. This no rewind policy is exactly why KMP is the linear time algorithm. Why does KMP win the performance war? Let's look at the graph. The red curve is the naive approach. As the text gets longer and the pattern more complex, the time actually grows quadratically. It's a steep, painful climb. The green line is KMP. It stays almost flat because its time complexity is O(n plus m). We spend OM to build the LPS table once and then ON to scan the text once. Because the text pointer never moves backward, every character in the text is compared a, a very limited number of times. KMP is a structural solution. It relies on the geometry of the characters. Its space complexity is OM to store that LPS array, which is usually negligible. If you're dealing with a static character set or cases where the pattern frequently repeats itself internally, KMP is our gold standard for stability. Now, let's switch gears and look at the solution B, which is Rabin-Karp. While KMP is about structure and geometry, Rabin-Karp is about mathematics. Think of Rabin-Karp as a fingerprint scanner. Imagine the text ABC. Instead of comparing A to A, B to B, and C to C, we run ABC through the hash function, a math formula that converts the string into a single number, let's say 5. Now, we pre-calculate the hash of our pattern. Then as we scan the text, we calculate the hash of our current window. If the pattern hash is 5 and the current window hash is 5, we likely have a match. The pivot here is simple. Don't compare letters, compare numbers. Comparing two integers is a single constant time operation for a CPU, whereas comparing two strings takes time proportional to their length. Rabin-Karp aims to make the search process as fast as a series of a simple math checks. You might be thinking, wait, if we have to recalculate a hash for every three-letter window, isn't that just as slow as the knife search? This is where the rolling hash comes in. Rabin-Karp uses a clever update mechanism. Imagine our window is A, B, C, D and it shifts to B, C, D, E. We don't re-add all the letters. It's all updating a running total on a receipt. We remove the old character, which is A, and we add the new character, which is E. This update happens in O1 time. Because we are rolling the hash forward, we can scan the entire text in linear time. We do the expansive character comparison only when the hashes match. This turns the window slicing process into a series of very fast arithmetic updates. It's incredibly efficient for scanning large documents where mismatches are the norm. Let's peek at the math behind the curtain. Rabin-Karp treats a string like a number in a high base, basically the alphabet size, such as 256 for ASCII. Excuse me. The formula treats each character as a coefficient in a polynomial, c1 by d to the power k plus c2 by d k minus 1. We use a large prime number like 10 raised to the power n 9 plus 7 to take the modulo y, because these numbers would otherwise become trillion of times larger than what a computer can store, causing an overflow. The modulo keeps our fingerprints within our manageable range. This math ensures that even a tiny change, like the change of an A to a B, completely changing the resulting hash number. It's a delicate balance of keeping the numbers unique enough to be useful, but small enough to be fast. Now, there's a gotcha. Math isn't always perfect in the context because of hash collisions. Imagine the words dog and God. If you have the same letter, just in different order, depending on your hash function, they might accidentally produce the same hash value. Say 42. This is what we call as a false positive. Because of collisions, Rabin-Karp follows a strict rule. If the hash pattern equals the hash window, then you must perform a manual character by character check to be 100% sure. We use the math to skip 99.9% of the text, but we use a character check to verify the final 0.1%. This ensures that our algorithm is always correct, even if the math occasionally produces a fluke. Always verify your hashes. While KMP is great for single pattern, Rabin-Karp is the true superpower in searching for multiple patterns at once. Imagine you are searching a text document for 100 different banned words. With KMP, you will have to run the entire algorithm 100 times, one for each word. That's slow. With Rabin-Karp, you calculate the hashes of all 100 words, put them into a hash set. Then you run the algorithm once on the text. For every window, you just check, does this current hash exist in my set? This makes Rabin-Karp the tool of choice for bioinformatics, which is looking for searching for the DNA sequences and plagiarism detection, checking if any part of the paper matches a massive database of existing work. Now, they scale horizontally across patterns in a way that structural algorithms like KMP simply just can't. So let's have a showdown. Which one should you use? KMP is a steel beam. It is guaranteed O n plus m. There are no collisions and it works perfectly every time, even in the worst case scenarios. However, it is significantly harder to implement correctly under the pressure of a 45-minute interview. The verdict for KMP is stability. Rabin-Karp is like a calculator. It excels at multiple patterns and has the beautiful O1 sliding window. It's generally easier to code if you understand the rolling hash logic. However, you have to deal with collisions, which can make it slow in rare, specifically engineered worst case inputs. The verdict for Rabin-Karp is versatility. If you're scanning for a single word, KMP is often safer. If you're building a plagiarism checker, Rabin-Karp is a clear winner. To wrap things up, let's look at the senior engineer cheat sheet. Remember that the naive approach is slow because it rewinds the text pointer and forgets everything it just saw. KMP solved this by the LPS array to skip ahead safely based on the pattern structure. Rabin-Karp uses rolling hashes to turn character comparison into fast numerical comparison. The golden rule is use KMP when you need a stable, guaranteed linear time for a single pattern. Use Rabin-Karp when you need to search for multiple patterns or are working in a field like bioinformatics. I hope this breakdown helps you master string matching. Explore CSAITTL for more DSA and interview prep content. Comment below and tell me which topic you want me to dive next. Good luck with your coding, and I'll see you in the next video.